Hello everyone, welcome back. Let me start with a quick scenario. Imagine you are a security guard at a bank. Your job is simple stop anyone suspicious from getting in. Now, imagine a criminal walk in every single day wearing a completely different face. Not a mask, an actual different face, different fingerprint, different height, different voice, different everything. How do you stop someone who never looked the same twice? That's exactly what modern Marvel does to traditional antivirus software. And today we are going to talk about how artificial intelligence is fighting back, how it is being used to detect Marvel that is literally designed to be undetectable. Alright, let's walk through something that both incredibly relevant and genuinely fascinating using machine learning to detect malware. Now, before you think this is going to be a dry technical lecture, it's not. We are going to walk through four completely different machine learning approaches, explain every single line of code in plain English, and then discuss what our result actually mean in the real world. Here is the big picture. When your antivirus software flag a file as dangerous, there is a machine learning behind that decision. Our project explore how different machine learning tackle this same problem and whether software is behaving maliciously or legitimately. We are going to cover four machine learning today. K means clustering, which discover pattern on its own without being told what's malware and what isn't. K nearest neighbor, which classify a file by comparing it to a similar file it already has seen. Random forest, which built an entire committee of decision tree and take a majority vote. Hidden Markov model, which watch how a program behave over time, step by step. Each one approached the problem differently, each one teaches us something different. Let's get into it. If you are new to the series and haven't watched the earlier videos yet, you will find all the links in the description below. Feel free to explore them at your own pace. There is no rush. You can always come back and watch them later by visiting the channel. But if you already have caught up, let's dive in. Today we are tackling something that sits at the intersection of cybersecurity and machine learning. Marvel detection using artificial intelligence. And we are going from absolute ground up. Here is what we are covering in this video. What Marvel actually is and why it matters at this scale we are talking about. How the most dangerous Marvel actively hide from the people trying to analyze it. Two completely different strategies for studying Marvel and why you need both. The structure of Windows executable file and why that structure is goldmine for the AI detection. How we safely extract meaningful data from those files without touching the dangerous code. And then for machine learning problem, each approaching the problem from different angle. By the end of this video, you will understand not what just these tools do, but how exactly they work. Let's get into it. First thing first, what even is malware? The word itself breaks down simply. Malicious plus software. Malware is any program that was intentionally built to cause harm. That harm could mean deleting or encrypting your files, stealing your personal data, spying on everything you do, or handling someone else's full remote control of your machine without you even knowing. It's not a bug, it's not an accident. It was written with a purpose. In May 2017, a piece of ransomware called WannaCry tore through the internet. Within just 24 hours, one day, it had infected over 230,000 computers across 150 countries. Hospital in the UK couldn't access patients' record. Telecom companies went offline. Banks frozen. The total estimated damage somewhere between 4 to 8 billion dollars. All of that from a single piece of malicious software. And ransomware is just one type. Malware also come as a spyware, Trojan, rootkit, botnet, worm, keylogger. It's designed to do something specific, but what they all share is intent. Someone built them to cause harm. Malware isn't a future threat. It is happening right now, continuously, at the scale most people never see. The very first computer virus was called Creeper. It was created in early 1917 on APRANET, the network that eventually became the internet. And here is the thing, it didn't steal anything, it didn't destroy anything. It simply printed a message on infected terminal that said, I am the creeper. Catch me if you can. The first antivirus program called Reaper was then written specifically to chase it down and delete it. Cybersecurity has literally been a cat and mouse game since the 1970s and it still is. Now, not all malware is created equal. The most dangerous and the hardest to catch are two different specific types, polymorphic and metamorphic malware. And the difference between two is actually fascinating. Let's start with polymorphic malware. Think of a chameleon. Every time it moves to a new surface, its skin changes color. The animal is same brain, same body, same behavior. But the outer appearance shifts constantly. You can't track it by color. That's exactly what polymorphic malware does. Every time it spread or replicate, it rewrite its own outer code using a built-in encryption engine. The malicious payload underneath stay the same, but the wrapper, the part antivirus scanner look at, changes every single time. Traditional antivirus relies on signature, essentially a fingerprint known as a virus. If fingerprint is different every time, the scanner can't match it. The malware slip right through. Now, metamorphic malware take this an entire step further. This is where it gets really impressive from a technical standpoint. Imagine a criminal who doesn't just change their outfit but change their bone structure, their fingerprint, their height, their walk, their voice, a completely different person every time, but committing the exact same crime. That's metamorphic malware. It doesn't just change the outer layer, it also rewrite itself from a scratch. The actual code body every copy is created is structurally different from the one before. Same malicious goal, completely different code. You are probably wondering, okay, so how does do we even detect something like that? Good question. Detecting metamorphic malware require what's called geometric detection, analyzing the shape and structure of code, not just its contained, the emulators which simulate what the code will actually do step by step without running into a real system. It's complicated, which is exactly why AI becomes so important here. One of the most studied example of polymorphic malware is Stormworm, which was active around 2007. At its peak, it had infected somewhere between 1 to 50 million computers worldwide, turning them into a botnet. Essentially, a zombie army of infected machines all taking command from a remote attacker. And its height, Stormworm was responsible for 8% of all global spam emails. That's not a typo. 8% of every spam message on the planet was coming from this one botnet. So we are not talking about simple program here. These are engineered system designed specifically to evade detection. All right. So we know what Marvel is. We know it can change itself, disguise itself, and fight back. The next question is how to even actually catch it. There are two broad strategies that security team use, and they approach the problem from completely opposite direction. The first is static analysis. You examine the suspicious file without even running it. You think of it as a study a crime scene, photograph, you inspect the evidence, you look for a clue, and you never actually go to the location. It's safe, it's fast, and it's controlled. The second is dynamic analysis. You actually execute the suspicious file, but inside a completely controlled, safe environment, like bringing a suspect into an interrogation room and watching every single move they make. You see real behavior in a space where they can't cause real damage. Both approaches have strength, both have weaknesses, and in practice, the best security system use both together. Let's look at each one properly. Static analysis means you never run the file. You treat it purely as data. Inspect its structure, read its content, and look for anything suspicious. Here is what actually look like in practice. Step 1, hashing the file. Your computer has typically SHA-256, a unique fingerprint of that exact file. If that fingerprint matches any known malware signature in a thread database, it gets flagged immediately. Fast, reliable, but only work for a thread that are already known. Step 2, inspecting the file structure. You look at how the file is built, which section does it contain, which system API does it call, what library it is calling on. Legitimate programs follow predictable patterns. Malware often doesn't. Step 3, pattern matching. Certain sequence of byte that are strongly linked to specific malware families. If you see those patterns, it's a strong signal something is wrong. Step 4, extracting strings. Raw text embedded inside the file, things like suspicious domain names, IP addresses, hard coded file paths, or even messages. Sometimes just one hard coded command and control domain give away an entire operation. Static analysis is fast and completely safe because we are never actually running anything. But here is the limitation. When malware is heavily packed or obfuscated, deliberately scrambled to hide its content, the file intent structure become almost unreadable. That's where static analysis start to lose its effectiveness, and that's exactly where dynamic analysis takes over. Static analysis isn't only used for malware, it's a core technique in software engineering used to find bugs, security vulnerabilities, and even licensing issue in code. Before a single line even run on a production system, it's the same concept applies across completely different industries. Dynamic analysis. Dynamic analysis does the opposite. You actually run the suspicious file, but inside a sandbox or a virtual machine. Think of it as a glass box. The Marvel thing it's running on a real computer, but you control everything surround it, and you are watching and recording every single thing it does. During dynamic analysis, you are monitoring two things: network behavior. Is the file trying to connect somewhere? Is it sending data out? Is it reaching out to command and control server? Are there DNS queries that shouldn't be exist? System behavior. It is creating a new file, modifying the Windows registry, spawning hidden process, attempting to escalate privileges. The biggest advantage here is that obfuscation stop mattering. Once malware actually start running and does its thing, you see the real action, not encrypted code. You see what it actually does, not what it actually like. The downside, it's slower, it's more resource intensive. And here is the part where this makes space genuinely interesting. Many advanced malware samples come with a built-in trick specifically designed to detect when they are inside a sandbox. And when they detect it, they go completely silent. So you run a Marvel in your control environment and it just sit there doing nothing, perfectly behaved, completely innocent looking. That lead us directly into the next section. Virus Total, the free online analysis tool owned by Google, submits every file uploaded to go through more than 70 different antivirus engines simultaneously, combining both static and dynamic analysis in one pass. It was originally created in 2004 by a small Spanish company called SpecSec. Here it where it get real interesting. Modern Marvel isn't just a malicious, it's smart. It know that analysis are going to try to study it. So it comes prepared, it has built-in mechanism specifically designed to detect when it's being watched and behave completely differently depending on the answer. Let me walk you through the most common anti analysis tricks. First, it acts completely normal at first. Some malware behave like a perfectly harmless application during its first run. The real payload is hidden behind a triggering condition, a specific date, a certain number of system restart, or a particular user action. Until that trigger fires, you would never suspect it. Second, it detects virtual machines. Malware actively check for sign that it's running inside of virtual hardware drivers, specifically registered keys, known sandbox process, unusual system characteristic. If it detects a virtual environment, it crashes intentionally, shuts itself down, or simply does nothing. Third, slow and low behavior. Instead of making a lot of changes at once, it spread its action across time. Small move, long intervals, nothing noisy, nothing that creates spike in system logs. Fourth, long sleep timer. Some Marvel literally call a sleep function for hours or even days before starting anything malicious. Most automated analysis systems have a time limit. They don't wait that long. The Marvel simply outlasts the scan. Fifth, it avoid non-signature. Marvel writer know exactly what antivirus tools scan for. So they continuously twerk and restructure their code to avoid matching any pattern in any database, not because they improve the code, specifically because antivirus tool would catch the old version. Now you are probably thinking, okay, how do you catch something that act completely innocent in a control environment? That is precisely the problem, and this is exactly why machine learning becomes so valuable here. Instead of looking for a one fixed signature, one specific fingerprint, a machine learning model learn pattern across thousands of samples. Pattern the Marvel can't hide, even when it's trying to behave. You can change how code look. You can't easily change what it fundamentally is. Some sophisticated Marvel sample actually monitor whether the mouse cursor has moved recently on the screen. Why? Because it is an automated sandbox. There is no real user sitting at the keyboard, so the mouse never moves. If the Marvel detects a stationary cursor, it assumes it's inside an analysis environment and goes completely dormant. Security researchers literally had to start building mouse movement simulation into their sandbox system just to trick the malware into revealing itself. And it goes even further. There are samples that only activate during specific business hours, others that only activate if the system language is set to particular region. That's how targeted and how calculated some of those attacks are. Now, let's talk about something really fundamental, something most people interact with every single day without even thinking about. Every program you run on a Windows, every .exe file, every .dll, every .sys file uses a standard structure called portable executable format, PE for short. It's the container format that the Windows operating system read to understand how to load, run a program. Think of it as a blueprint the OS follows every single time you double click an application. And this structure, this blueprint is exactly what malware loves to hide. Think of P file like a building. Every building has a layout, a fundamental, floor, rooms, a purpose for each space. The P file works like the same. At the top, you have a header. This is the metadata, the blueprint for the whole file. It contains the DOS header, the P header, the optional header, the section table. Together, these tell Windows everything it needs. Where does this program start? How much memory does it need? What external dependency does it have? Below that, you have a section, the actual content of file, the code section that holds the executable instruction, the actual logic of program. The important section lists every external function the program need from Windows system libraries. The data section hold variable resources and embedded content. Malware typically hide its malicious code inside the binary image section, disguised as what look like a normal program data. To spot it, you need to understand how a legitimate building is supposed to be structured. So you notice when something doesn't belong. Now, here is why this matters specifically for us. Once we understand the structure of P file, we can extract specific numerical values directly from headers. Values that describe the file, its entry point, its versioning information, its linker details, and those values we feed them directly into machine learning model. This is the bridge from cybersecurity to artificial intelligence, and we are about to cross it. Every single PE file on Windows still carries a small relic from 1980s. Buried inside a DOS header is a tiny embedded program that simply prints this program cannot be run in a DOS mode, a system from the era where Windows and MS-DOS had to coexist on the same machine. Nobody run MS-DOS anymore, but that line, that relic, is still sitting inside virtually every Windows executable on a planet. Decades later, legacy code never really dies. All right. So at this point, we understand PE files. We know what they are, how they're structured, and why malicious malware hide inside them. But here is the problem. Machine learning doesn't understand the binary. It doesn't understand the raw executable file. It understands the numbers, tables, structured data. So before we can use AI to detect anything, we need to translate those files into format that model can actually work with. Now, we are not going to dump entire malware sample into machine learning model. That would be dangerous and also completely impractical. What we are going to do instead is extracting those four specific numerical values directly from the P headers, metadata that describe the files using those numbers as our input. Think of it like a doctor reading a patient's lab report. The doctor doesn't need to know the entire medical history, your childhood photos, or your daily diary. They just need a few key values: blood pressure, sugar levels, temperatures, and those numbers alone can already tell a very clear story. That's exactly what we are doing here. Four values: clean, safe, and surprisingly powerful. So, what are those four values? Number one, address of entry point. This is the memory address where the program began executing. The very first instruction the operating system run when the file launches. Legitimate program have predictable standard entry point.
Malware, especially packed or obfuscated malicious, often has unusual or out of range entry point because real code is hidden somewhere else and tiny loader run first. Number 2, major image version. This is the version number of executable image itself. Sometimes malware carries mismatch or unusual versioning, a kind of fingerprint that separate from genuine software. Number 3, major linker version. This tells us which linker version was used to build the file. Some malware families are consistently compiled with outdated or uncommon tool chains, and that pattern show up in this value. Number 4, major operating system version. The minimum OS version the file expect to run on. If the value look inconsistent or unusual, give the rest of the file, it become a meaningful signal. None of those values individually scream malware, but together as a pattern across thousands of files, the AI model learn exactly what a legitimate combination look like and what a suspicious one look like. Now, here is a safe workload for the extracting this data. First, we are work inside a control environment, a virtual machine, an isolated lab system, never on your production machine. Second, place your sample executable file in a dedicated folder. Number 3, use Python with the pre-file library to open each file with p header and extract 4 values. 4, save everything into a clean CSV file. That CSV file our entire machine learning dataset, not malware code, not dangerous binary, just numbers in rows and columns. In large cybersecurity companies, pipeline exactly like this run continuously 24 hours a day. They extract metadata from millions of submitted files every single day and feed that data into constantly retaining models. Every new malware family that get caught makes a new model slightly smarter. The idea is simple, but the scale at which it operates is genuinely staggering. Before implementing the machine learning model, the first step was setting up our development environment and preparing the dataset. Our experiments in this project were developed and executed using Jupyter Notebook, which provide an interactive environment for writing code, visualizing output, and analyzing results step by step. This make it particularly useful for machine learning project because we can observe data transformation, model training, evaluation metrics, and visualizing in a structured workflow. For the first 3 machine learning models, K means clustering, K nearest neighbor, and random forest. We used the PE files malware dataset obtained from Kaggle. This dataset contains feature extraction from the portable executable or PE files, which are standard executable file format used in Windows operating system. Each record represents a software file and includes various characteristics that help distinguish between legitimate application and potentially malicious programs. The dataset also contains a target label indicating whether the file is classified as a malware or banning, making it suitable for both supervised and unsupervised learning experiment. For the hidden Markov model experiment, we use a different dataset known as malware analysis API call sequence dataset. Unlike the previous dataset, which focus on static file features, this dataset captures sequence of API calls generated during program execution. This API call sequence provide insight into behavior of software over time. Since hidden Markov model are specifically designed to analyze sequential pattern and statistical transformation, this dataset is well suited for behavioral malware detection, allowing us to identify malicious activity based on order and structure of action performed by program. Alright, let's begin with the k-mean. We start with 100 of unlabeled network sample, each one a PE file described by 2 behavioral pattern, entropy and section count. No one has told us which file are malware. These centroid marked with X are dropped at random position. Every sample measure its distance to each centroid and join the closest one. Watch the color appear. Blue, red, green. Clusters are begun to form. They are rough and overlapping, but structure is already emerging from nothing. Now, each centroid relocate to the mean position of its assigned group. The dashed trails show you exactly where they have traveled. Assignment are recompute. Sample may switch cluster. This cycle repeat tightening the groups with every pass. The centroids stop moving, cluster have stabilized. What you are left with are 3 distinguished behavior group. One banning, two potential malware families, and discover the entire without the label, the third one. That's the power of k-mean. pure structure from raw data. K-mean was invented by Stewart at Bell Labs in 1957, not for machine learning but for compressing telephone signal. It wasn't even published publicly until 1982. The same algorithm that was built to squeeze phone calls is now being used to group malware. It's over 65 years over and still one of the most widely used clustering algorithm in the world. Now let's discuss about KNN. The scatter plot show us the entire label training set, blue, red, and green dots, representing three known category of network traffic. KNN doesn't build a model from this. It simply memorizes each single point. The algorithm is lazy by design. A new unknown packet appears that the black star. The algorithm measures distance from to every stored sample in the database. Then it selects the seven nearest neighbor. Watch the circle appear one by one as the closest points are identified. Now in majority votes, seven neighbor, seven votes. Which classes hold the majority win the label. The decision is purely local. Only the immediate neighbor matter. No global structure, no assumption. KNN is intuitive, interpretable, and surprisingly effective for defecting anonymous traffic pattern. K equal to 5 is a solid, reliable default for most problems. One critical rule, because KNN uses the distance, feature must be on the same scale. If one feature is in the million and another is between 0 and 1, the large feature will completely dominate the distance calculation and make every other feature meaningless. That is why we scale the data first. KNN is officially called a lazy learner in machine learning because it does zero computation during training. It just memorizes the data. All the heavy lifting happen at the prediction time. When you are working with millions of files, that can become expensive, which is why engineers often use optimized structure like KD trees to dramatically speed up the neighbor search. Same algorithm, just smarter look. Now, on the step one, the forest is built. A random forest starts by growing many independent decision trees. Each tree trained on a different random bootstrap sample of data. At each split, it only considers a random subset of feature. This intentional randomness is what makes the assembler robust. Step 2, query the forest. A new unknown PE file arrived, the diamond walker. We send it down every tree simultaneously. Each tree on the step 3, all 9 trees have voted. The majority class win the final labor. Where any single tree might overfit or make a mistake, the assembler correct itself. More trees, more stabilization. Random forest doesn't just classify, it resists the noise that fools simple model. Random forest was formally introduced by Leo in 2001 and consistently ranked in the top 3 most used machine learning algorithm in the industry. It was used by winning team in the Netflix prize, a $1 million competition to improve recommendation accuracy. The exact same algorithm that helped recommending movie is also used to catch malware. And in the medical research, random forest model has achieved diagnosis accuracy rivaling trained specialists just from numerical test result. Hidden Markov process. In the step 1, what we are watching is a sequence of API call emittance by the running process over time. The color of each point reveals the true hidden state. Blue for banning activity, red for suspicious, green for malicious. But in real system, those states are invisible to us. We only observe the call values. This is what separates HMM from other classifiers. The model understands that behavior unfold over time. Each state influences the next through a transition matrix. A process drifting from banning to suspicious to malware tell a story. And that temporal pattern carries far more signal than any signal snapshot. Next, to classify a process, we train two HMM and one on banning behavior, one on malware. We then score the observed sequence against both model. Which model assign the highest log likelihood wins. Everyone, so as you know that this video has become very long, so I have divided it into two parts. If you need to watch the second part regarding the coding, I have added the link in the description for the Udemy, and thank you so much. All right, let's bring all together. We have now run four completely different machine learning approaches on malware detection, and each one taught us something different. K-means clustering show us that the malware and banning software has naturally distinct fingerprint. A silhouette score of 0.91 Remarkable for unsupervised learning. The limitation was class image, 75% of dataset being malware, and the smaller banding population couldn't form its own clear cluster. The insight stand. The data has real exploitable structure. And that brings us to the end of this session. Thank you for staying with me and walking through this complete machine learning workflow. I hope this tutorial helped you to understand not just how the code works but also the intuition behind each model and how we can apply different machine learning technique to the same real world problem in a different way. If you found this helpful, feel free to leave your question in the comment section below. I will be more than happy to help you out or clarify anything you might be stuck on. Also, don't forget to check the course link in the description. You will find the full source code of this entire project along with the additional learning material that are being updated regularly to help you go deeper into machine learning and cybersecurity application. Thanks again for watching and I will see you in the next one.